Our question says, calculate the current I in the circuit below. And we have a circuit there. You can see that we have a 17 volts battery source, and then we have that battery has inherent in it resistance, internal resistance of 0.2 ohms. Then we have some series of batteries of resistors there. So remember, according to our series connection, if we have a group of batteries, let's say a group of resistors connected in series, say R1 and R2 as drawn now, and then we have current flowing from one point of that circuit to the other. The current, say if I1 is the current that passes through R1 and I2 is the current that passes through R2, for resistors in series, I1 will be equal to I2 will be equal to I, telling us that the same current will pass through resistors when they are connected in series. Please just take note of that. Now, if we also have voltage V moving from the same point there, remember that we said that R equivalent is equal to R1 plus R2. That is for series connection. R equivalent is equal to R1 plus R2. That is the way we add resistors in series. Now, if we have a source of voltage too flowing from the our left hand side to the right hand side of this our drawing there, we have that the voltage across R1 is V1 and the voltage across R2 is V2. Now, if R1 and R2 are not equal, it means that V1 is not equal to V2. And then R1 and R2 are not what? Equal. V1 is not equal to V2. That's for series connection of resistors. Let's take note of this. But if R1 is equal to R2, then V1 can be equal to V2 for series connection. Voltage is not equal, provided the resistors don't have equal resistance. Now, let's look at when we connect resistors in parallel. What happens when we connect them in parallel? So let me just give a drawing of a simple parallel connection. We have something like this. Okay. And then this is how we draw parallel connection. And then we have a source of voltage from our left hand side, and then we have a source of current also from that left hand side, and then we have R1, and then we have resistor R1, and then we have resistor R2. So for parallel connection, we have a node. We always have, anytime we have a node, it shows that we have a parallel connection. When our current gets to that node, the current will split into two, I1 and then I2. I1 is what passes through R1, and then I2 is what passes through R2. So if R1 is not equal to R2, then it means that I1 is not equal to I2. There's a split there. So I1 plus I2 is actually equal to I. It is that I that divides into 2. This I that was here will split into 2, I1 and I2. And then based on this particular formula written here is what Kirchhoff's law is all about. Kirchhoff's law states that the algebraic sum of current in a node is equal to 0. And remember, I said when I1 is not equal to when R1 is not equal to R2, then I1 is not equal to I2. So let's take note of that. Also, but when we are talking about the voltage now, if we have V1 passing through R1 and V2 passing through R2, for parallel connection, V1 will be equal to V2 and will be equal to V. So for parallel connection, the same voltage passes through the resistors, but the currents are not the same. The currents will split. That is for parallel connection. And for equivalent resistance, we are given that for finding the equivalent resistance of these two resistors, we'll just take the we look for the LCM of R1 and R2, that's the LCM of R1 and R2, then we multiply it together, that's R1 times R2 over R1 plus R2 gives us our formula for finding the equivalent resistance of parallel resistors. So we should take note of this. For series connection, we know that the current is equal, but the voltages are not, except the resistors have equal values. But for parallel connection, the voltages are equal and the currents are not, except we have the resistors of equal value. So let's take note of that. We can note that down somewhere, and then we can now go into solving the question on our screen. So let's look at that screen again. Let's look at that again. From what we have on our screen, we have a battery with a source of as our source of voltage, and that battery has inherent losses as a result of internal resistance, and our internal resistance is 0.2 ohms. I can decide to take the 0.2 ohms from the battery and just move it somewhere. I can move it because this internal resistance is actually in series to the circuit. So I can decide to move that internal resistance and draw it here. Let me just draw it here, and then I call that 0.2. So that 0.2 ohms is in series to the rest of the circuit. From that, we have a current moving from here. This current, because it's in series, the current, the same I1, will move till it gets to the node, the first node on our circuit. So that 0.2 ohms is in series to the rest of the circuit. I would look for a way to write down a formula that depicts the total connection that we are seeing here. Then we'll resolve it together from there. So we have that 0.2 ohms is in series with the rest of the circuit. And now we can write our R equivalent to be equal to 0.2 in series to the rest of the circuit. I'll just put a bracket there. So we have then we have a node there. When the current gets to that node, I said when anytime there's a node, we talk about a parallel connection. The current will split into two. One goes down to the 9 ohms resistor, and then the rest goes to the 15 ohm resistor. This tells us that the 9 ohm resistor is in parallel to the remainder of the circuit. So this line is where, from this line down to the right hand side, is in parallel to the 9 ohms resistor. So that will be 9 parallel the rest of the circuit. Let me open a bracket for the rest of the circuit. And then we have next the 15 ohm resistor. That current will pass through it because there's no node along there. So it will pass through the 15 ohm resistor until it gets to the next node, as I've circled there. So it means that the 15 ohm resistor is in series with the remainder of the circuit. That is 15 plus, remember, series connection we just add. So 15 plus the remainder of the circuit. So I'll open a bracket for the remainder of the circuit again. And then we have that node there. When current gets to that node, what happens? It splits into two again. One going down to our 8 ohm resistor, and then the other going to the 19 ohm and coming to the 5 ohm resistor. There will be no split there because there is no node. So it means that the 8 ohm resistor is in parallel to the rest of the circuit. So that will be 8 parallel 19 is in series to 5. 8 parallel 19 plus 5. So I can close that bracket. Close the other bracket for the 8, the one for the 15, and then the one for the 9. Good. Now that I've written this formula, I would like to label my formula. Let me call the inner one. I'll be working from inside. Let me call the 19 plus 5. Let me label that R1. So I'll call 19.5 R1. Okay, let's look at something that is happening here. From here now, we have the current meeting at the download, the kind of back going back. Then it comes to this 2 ohm resistor. So the 2 ohm resistor is in series because all the current will meet at the nodes there. So the 2 ohm resistor is in series with the whole remaining of the circuit. That's what that means. So I will now add plus 2. The 2 ohm resistor is in series to the rest of the circuit. So I can just I would like to label this my internal brackets. I'll call that R1. Let me call from this side, from the 8th spiral to the other rest of the circuit, let me call that R2. And then 15 in series to the rest of the circuit, let me call it R3. And then let me call 9 in parallel to the remainder of the circuit, R4. So let us label ours like that. When we are working, we make our work neat. Now, I can say that R1, let me go ahead from solving R1 to R2 to R3 to R4 like that. So R1 would be equal to 19 plus 5. R1 will be equal to 19 plus 5, and that is going to give us 24. So R1 is equal to 24 ohms. Then R2 is 8 in parallel to 24 ohms. 8 parallel 24. That would be 8 in parallel to 24 ohms. That's what we said there. 8 in parallel to the rest of the circuit. So R2 would be equal to 8 parallel 24. And that is going to be equal to 8 times 24 over 8 plus 24. This would give us 8 times 24 over 32. Over 32. 8 into 8 is 1. 8 into 32, it will give us 4 times 4 into 4, 1, and 4 into 4 is 6. So that will give us 6 ohms. Then we can go ahead and solve for R3. R3 is equal to 15. R3, look at R3. The R3 is 15 in series to the remainder of the circuit. So that will be 15 plus the equivalent of the remainder of the circuit is 6 ohms. That will be 15 plus 6. 15 plus 6, because we've already said that the remainder of the circuit equivalent is 6 ohms. So that will be 15 plus 6, which is equal to 21 ohms. Then we can go ahead and solve for R4. R4 is going to be equal to 9 in parallel to 9 in parallel to the remainder of the circuit. 9 parallel the remainder of the circuit, and that will give us 9 times 9 in parallel to the rest of it, which is 9 in parallel to 21. That will be 9 times 21 over 9 plus 21. So this will be equal to 9 times 21 over 30. 3 can go into 21 7 times, and 3 can go into 30 10 times. So this will give us 6.3 ohms. 6.3 ohms. So R equivalent is going to be equal to 1, that's for the internal resistance, 1, that's 0.2, that's a small r 0.2 plus 6.3 plus 2.0. R equivalent is 0.2 plus 6.3 plus 2.0, that's 8.5 ohms. Therefore, remember that we said that V is equal to 17 volts. V is equal to 70 volts, and we have that R equivalent is equal to 8.3 8.5 ohms. According to Ohm's law, I is equal to V over R. I is equal to V over R, so that I will be equal to 17 over 8.5. 17 divided by 8.5 is 2. So I is equal to 2 amps. Solved. Our next question says, for the circuit below, find I1, I2,